Hi, welcome to Principles of Energy, Module 4. We're going to talk about thermodynamics, and specifically the thermodynamics meaning heat that goes into the system, i.e. also known as frictional force, in the way that we're losing it in the form of work. And so one of the main things we need to just start by talking about is temperature, which is a measurement of the amount of energy within the molecule. It's how fast the molecule is vibrating, and everything has energy, and so it's vibrating at particular speeds, and the faster they vibrate, the higher the temperature will read. So at this moment, I would like to just point out the three major temperature scales: Celsius, Kelvin, and Fahrenheit. Celsius is System International, and it's the good scientific way. And if you're going to work in a lab doing energy analysis in the future, you will be using Celsius. If you do not want to work in negative numbers, you will use Kelvin because you have absolute zero, and nothing moves at absolute zero. It's the point where no molecular motion is present. And then we go up from there. So there is no negatives in Kelvin. And then Fahrenheit, which is a funky system that has a very difficult history. And if you're interested, look it up. It's an interesting read. It's kind of funny. And of course, in the United States, if you're working on job sites, standard construction sites, doing energy analysis in a home, you will be using a Fahrenheit system. And I will show you equations that work with both Celsius and Fahrenheit later on in the chapter. Now, with that said, you have an additional video. It's produced by the Discovery Channel, and I think you'll find it very interesting. And that one's going to talk about what is cold, and that there's technically no such thing as cold. There's just the act of heat stealing that's happening. And so if you would like to take a moment to pause and flick over to that video now because you're interested, go for it. Or if this won't distract too much, please feel free to continue on with this video and then watch that one after. This is just an image giving you those temperature scales again. You can see Celsius lining up, Kelvin lining up, and then Fahrenheit, which is not based on water in any capacity, on its funky 12 scale in its little system there and how it lays out. And so once again, Celsius scale based on water, something that can be found universally, has the freezing point at the point where it changes phase, Newtonian phases of solid, liquid, and gas. And so solid water, liquid water, and then after 100 goes to gas form water. Energy units and conversions, just as a reminder, 1 joule is the unit of energy equal to the force of 1 Newton acting on 1 meter. 1 watt, which is the power within the system, is a joule of energy per second. So that's actually second triplicate when you look at the breakdown of the equation for watts. And down below is a little image of a simple battery built with the magnet and the little Duracell. And obviously, if we had a little energy lab that we had to do with this course, this would probably be one of those little lab experiments that we would do. I'd have you construct your own mini battery system. Quick equation for power. To find the power of an item, you take its current times its voltage. And so down below, we can think of 1 watt of power from a current of 1. Amperes is the flow through a voltage of 1. Kilowatt is 1,000 watts. 1 kilowatt hour is the energy of 1 kilowatt of power flowing for 1 hour of time. And that can be expressed as E is equal to P over times T, and this T being lowercase means time. And it's set, capital T is thermal. Keep those things straight because they're important for our equation uses. And then 1 kilowatt hour, or kWh, can be expressed as 3.6 times 10 to the 6 joules, or 3.6 million joules. It's another way of saying, right? So nice scientific here, and then just written word form here. Now, specific heat. Specific heat is the amount of energy needed to raise an item's temperature. For example, 1 calorie is the heat and the amount needed to raise 1 gram of water 1 degree centigrade. So a calorie is based on water, and it's based on specific heat. So 1 calorie is another way of saying this is the amount of energy necessary to raise something's temperature. Yes, calories does relate to food, except for food, which we call calories, is actually kilocalories. To think that an apple would be 0 calories is nonsense. It's just under 1,000 actual physical calories. So it's under 1 kilocalorie would be the actual weight. So food calories and calories are relational, but technically food calories are kilocalories. But food provides energy, right? We're little machines. So British thermal units, which is the US system that we do use. Once again, this is more the construction site. So scientific site on this little bit, construction site on this little bit. British thermal unit is the amount of heat necessary to raise 1 pound of water 1 degree Fahrenheit. And that, once again, is a definition of specific heat. It's the amount of energy necessary to raise the item's molecular state to a more active state, to more motion. 1 British thermal unit is equal to 1,055 joules. 1 BTU, or British thermal unit, is equal to 252 calories. It's also equal to 1.055 kilojoules. 1 quad is equal 10 to the 15 BTUs. So when you see something written in quads or therms, they are referring to the British thermal system. It's not Science System International. It's not the calorie system. So just be careful in the future. While I won't do that to you in this course, making you do equations that extreme with quads and therms, it's something to keep in mind because you will run into quads and therms. They're talking about multiples of BTUs. And then 1,000 kilowatt hours is equal to 3.41 million BTUs. Once again, a BTU is about the energy of 1 really good matchstick. So if I took 1 matchstick and I burnt it, that energy that would be released in light and heat would be equivalent to 1 BTU. Talking about the importance of temperature and the ability to control thermal equivalence. This little graphic gives us a bit of what we use energy for within the home. And so right here we can see that heating takes up 41% of our home energy use, and then producing hot water is 20% right there. Cooling, our AC systems, and this graphic's a bit old. I would say it's actually higher. It's more around 12% now, especially in the United States. It's more around 12% of the pie in cooling now. And then just your appliances and things is down here in your 31. And so breaking off that heating bit, what do we get the energy from to heat our homes? This is where we come into this little bit on this side. Electrical is the biggest slice with gas up there. Home heating oil, petroleum or liquefied propane, right? This is what they're talking about when they say liquefied petroleum gas. They're talking about propane heating of the home. And then wood heating of the home. So this is where this little cut in comes in. Similar graphic giving you the importance of various items in controlling temperature and temperature-based equipment within the home. The kitchen appliance being the biggest set, we're talking about the refrigerator. So understanding how to equate and work with temperature systems is very important because then you can create applications for the law of conservation of energy, making it work really efficiently. So that brings us into the laws of thermodynamics. So first law of thermodynamics, it basically says that work is done on a system plus heat added to a system is equal to some change on that system, which should feel very intuitive, right? Basically, we're saying that matter and energy can change in form based on its mass, its quantity, and the work done on that system. And so down here in this little equation, it's work on the system plus Q2, that's heat. Q is specific heat or thermal heat to a system equals change, right? The little delta system symbol is a change symbol. Kinetic energy plus potential energy plus thermal energy. Once again, capital T is heat, thermal. And that is equal to the little delta or the change in energy total. So I'm going to pick up with thermodynamics' second law now in a part 2 for this video.